We're live.
Hi, everybody. Welcome to the evening session of QMAT 2021 on the second day. Our chair today is Professor Subrata Mukherjee from Indian Institute of Science, Bangalore. And I will hand over the session to him. Over to you, Subrata.
Okay. Thank you very much, Rajdeep, and welcome everyone. So this is one of the two concluding sessions of the day, and we have three speakers on this session, each of whom is going to give a 30-minute talk. So I'd like to remind the speakers that there will be 5 minutes of questions at the end of their talks and no questions during the talk. So what I will be doing is I'll be giving each speaker a signal first at the end of 20 minutes and then at the end of 25 minutes. So that they can pace themselves and also wind up their talks accordingly. Everyone in the audience, please keep yourselves muted and your cameras turned off unless you want to ask a question. As I said, questions will be at the end of the talk. When you want to ask a question, you can either use the raise hand tool if you know where that is. If not, you can just unmute yourself and ask a question. Okay. So with that, I'd like to invite the first speaker of this session, Amit Agarwal from IIT Kanpur, and he's going to be talking about interband and intra-band plasmons in flat bands of Moire superlattices.
Okay, so thank you for this invitation, and thank you for coming to hear this talk. As I already said, I'm waiting to be heard. Right. So I'm going to talk about plasmons in flat bands of Moire superlattices, and most of this work has been done by Atashi and Devashish, but I get to talk about this basically. Okay. So this is Devashish here in this very old photograph. Okay. So let's go ahead. Okay. So just to introduce the activities in my group, some of you may not be familiar with. So we generally talk about novel quantum materials, so topological materials, 2D, new 2D materials, transport, excitons, optical physics in them, Berry curvature or quantum geometry induced, let's say, electrical transport and optical properties, and new collective modes basically. Okay, so this talk will primarily be about this new collective modes or collective modes, let's say. Okay. Okay. So what is the excitement about Moire superlattices? Okay. So the excitement predominantly, so apart from theoretical ideas which were there earlier, recently started from this Nature paper, which demonstrated unconventional superconductivity in magic angle TBG basically. So twisted bilayer graphene. And the idea has been earlier in a lot of papers, etc., trying to get the band structure right, etc. The most established method basically roughly comes from this paper, which was 2011. So Alan McDonald's group basically. Okay. And these are more recent some examples of work which highlight some important aspects about the band structure or origin of magic angles, etc. Okay. So what is the excitement basically? So to the broad audience who are not familiar maybe with this, so Moire superlattices have tunable electronic properties. So these are 2D. So graphene on top of graphene, slightly rotated, etc. So I can apply gate voltage and I can tune the, so I can have a back gate and a top gate, and I can tune the, let's say, the doping. So the amount of filling that I have in the bands, and I can also tune the vertical electric field that I apply, and which modulates the band structure. So that's the one of the most exciting things about this. It has tunable electronic properties. And angle of twist, vertical electric field, substrate, or stacking sequences, etc., can serve as external knobs which tune this electronic, optical, and other properties, of course. Okay. These systems have, by magic, extremely flat bands, flat in the sense of having a bandwidth of roughly 10 MeV, which gives rise to Van-Hoff singularities in the DOS. Basically, so the whole of the spectral weight is concentrated in a very small region of energy, so which is Van-Hoff singularities. Okay. And they have topological properties. So the bands are topological in nature. So they do not break time reversal symmetry. So the global Chern number is 0, but you can define what is called a Valley Chern number in these quantities, and that defines the topology of these. They, because of Van-Hoff singularities, they can display strong correlation effects. And the combination of strong correlation effects and topological properties can give rise to exotic superconductivity, exotic magnetic states, and so on and so forth. And in addition to that, these are also playgrounds for a lot of band geometric related physics, basically. So which arises from Berry curvature, quantum metric, for example, etc. And strain plays a very important and nice role in this because strain can give rise to what is called local time reversal symmetry breaking in this system, in a sense of synthetic gauge fields, etc. Okay? So this is roughly a very broad summary, and a very nice review article on some of these aspects is by Alan McDonald in this recent Nature Materials review, basically. Okay. So let's go ahead. So our excitement, so my group's excitement in this field started from working with friends from TIFR to probe some nonlinear transport properties in this class of materials, basically. So we will take another brother of TBG, which is twisted double bilayer graphene. Okay. So we were probing non-linear, so second order Hall effect, anomalous Hall effect in these materials, and we found that these are intricately connected to the band topologies, etc. So by tuning the vertical electric field, we can change the band topologies, and this second order nonlinear Hall effect actually shows peaks around those band transition points, etc. Okay. So that was something which got us started in this field. Okay. So I'll skip these details, etc. But carrying on that excitement, we will talk about plasmons in the systems today. Okay? So just to give you a very broad overview of plasmons. So plasmons, you can think in terms of bulk plasmons, which appear in metals or in dopes, conductors, etc. Something we may study in Kittel, for example, right? So plasma frequency, optical frequency greater than plasma frequency, you have full transmission. Optical frequency is less than plasma frequency, you have reflection and partial transmission, etc. Okay. Then, so that is bulk plasmons. Then you have surface plasmons, which can come from these bulk plasmons, which are getting terminated at the surface, and they interact with electromagnetic waves, etc. Can give rise to surface plasmon polaritone. And nowadays, because we have this topological materials, etc., so they have the surface states, etc. So they are like 3D bulk is gapped. On the surface, you can have let's say charge density or electronic states, and they can give rise to another kind of surface plasmons, so which is not captured here. Let's say. Okay. And then we have these nanoparticles. So let's say 20, 40, 100 nanometer rods or spheres, etc. They generate this localized surface plasmons, which are very useful from practical applications. So light can interact with them, and they are used for thermoplasmonics, local heating, local detection of radiation, etc., etc. So technical applications, etc. But that's the broad, let's say, plasmons. Okay. So I'll predominantly be talking about bulk plasmons, and the simplest way to understand bulk plasmons is via classical, let's say, theory. So Newton's law, force is equal to ma. On the left hand side here, I have, let's say, m times dv by dt, and v is directly proportional to the current, let's say, charge, the particle current. Okay. So m times dv by dt is given by, let's say, the total density plus I have a gallium, and whatever density fluctuation I may have in the system, that interacts with the background density to give rise to this kind of a force, basically. Okay. So if I take this equation, I have a current here, I have a density here, so I need to bring them on the same footing. I can do that by using continuity equation. Dou rho by dou t plus divergence of current is equal to 0. Charge conservation, and I do a Fourier transform, I'll immediately end up with this kind of an equation, which says omega square minus n by m, m being the effective mass, etc., times q square vq. Vq is the Fourier transform of whatever Coulomb interactions are there in the system. Okay. And this implies that, as soon as this quantity in the bracket is 0, I can have large density fluctuations in the system. Okay. And these large density fluctuations are, plasmons, basically, which can interact with the light and so on. So this gives you exact plasmon dispersion in the long wavelength limit. So this in generic, general n by m q square times vq, which in 2D specifically, vq becomes 1 by q. So it has this particular form. And I just wanted to highlight in 2D, these plasmons, which are called as bulk intra-band plasmons, disperse as root q, basically. So omega is proportional to root q. Okay. So that's a classical theory. And you can go ahead and talk about same argument in different dimensions, 1D, 2D, 3D, etc. The only thing which changes is the Fourier transform of the Coulomb interactions. And if you do them correctly, then you get this basically. So 3D plasmons are gapped, 2D plasmons are root Q dispersing, which I already described. And 1D plasmon disperses Q times this square root of Bessel function, which roughly behaves like a log of QA. So Q times log Q, let's say, that's 1D plasmon dispersion broadly. Okay. Okay. So this was a very classical argument. How do I think of them? Quantum mechanically, etc. Okay. So quantum mechanically, the idea is that I need to calculate what is called the density response function of the system. So the interacting density response function of the system, which is quite hard thing to calculate, let's say, but I can do some approximations. And what we are going to use here is one of the approximations, which is called random phase approximation. Okay. So essentially, what we do is we just keep the Hartree terms in the series of all diagrams possible, basically. So we calculate the non-interacting density response function. So there is a node rho, another node rho connected by a Green's function line, another Green's function line. So we calculate this bare diagram. This is just chi0, and I keep this chi0 ring diagrams, etc., which are connected by single interacting lines, and I sum over all possibilities. I get this particular density response function. Okay. And so this is the interacting density response function, RPA, which is just keeping the Hartree terms and doing the approximation, just is chi tilde, just replaced by chi0. Okay, that's it. And the denominator here is called the RPA dielectric function, and it generally accurately captures the plasmons in a lot of materials, etc. Okay. So it is quite widely used and generally sufficient to describe this collective behavior of electrons in a sense of plasmons, basically. Okay. So if you take this and do a calculation, explicit quantum mechanical calculation also for, let's say, a parabolic electron gas, you will find that this chi0 in the long wavelength limit goes like this, which again gives you the same plasmon dispersion that we got from a classical limit. Okay. So that's one. Then, so just to motivate some of our work on collective excitations in this thing. So we recently probed some 3D Dirac plasmons in type 2 Dirac semi-metal. Then we proposed a new plasmon mode in a type 2 Dirac semi-metal. More recently, this paper is under review, where we find a lot of EN zeros, basically. So epsilon near zero conditions or topological phases in light propagation. In the same material but different frequencies, etc. in NIT2, etc. Okay. So then let's get back to plasmons in Moire superlattices. Okay. So again, plasmons and these are interesting because of tunable properties, angle of twist, etc. Can serve as external knobs. Van Hoff singularities are there that can give rise to some new properties of plasmons. Low bandwidth systems means they can have low frequency plasmons, which may have some technological applications we do not know. Then can topology and plasmons be intertwined? No, so that's a question we as of now do not know. Okay. Okay. So specific to plasmons, starting from there, what is the nature of intra-band bulk plasmon? Goes as root Q, of course, but what are the prefactors, etc. Do they support any other kind of plasmon modes? So they are very flat bands, very close to each other. So interband plasmon modes, can they support? What is the origin and nature of this interband plasmonic excitations? Okay, so of course the answer to the previous question is yes. That's why this question comes. Then can there be some new kind of acoustic plasmon modes in the systems? Then are there possibility of, let's say, plasmon modes, 1D plasmon modes along the domain walls or along the edges of these kind of Moire systems? So these are the kind of questions which sort of motivated us before we started. Okay, and there have been some recent studies on plasmons in these kind of systems, particularly this paper by Levitov pointed out that you can have very interesting plasmons in the systems which can exist in a very narrow flat bands, etc., and which are long-lived, etc. Then this paper was about plasmons at the edges, basically. So they form a network flowing along the interface of AA and AB stackings, basically, and they can form sort of a Dirac cone like structure in the plasmonic dispersion and so on. Okay, and this is a recent paper where they probed some experimentally. They probe some higher energy interband plasmons. Okay, so let's come back to our calculation. So how do I calculate? So my scheme of calculation is really simple. As I just described, we'll calculate the non-interacting density correlation function. We will use the RPA approximation to calculate what is called the energy interacting response function or the energy loss function. And then peaks in that energy loss function will give me signature of plasmons, basically. Okay. So for those of you who like equations, I start from here. I calculate the dielectric function, which is given by this, which also gives me the non-interacting response function, interacting response function. But for calculating the loss function, it's just given by -1 by imaginary part of 1 by epsilon. And this energy loss function is captured by electron energy loss experiments, basically. So if you do accurate enough experiment, then you can actually, the peaks in those experiments correspond to exactly this quantity, basically. Okay. That's the idea. Okay. So some more details about how we calculate. So let me skip. So brief description of band structure. So, you have one bilayer graphene. You have one bilayer graphene. They're slightly rotated with respect to each other. So the brilliant zones are slightly twisted. Then within this twisted brilliant zone, you can define the new brilliant zone of this Moire structures. You take this and you construct this, smallest Hamiltonian, which will not give you accurate enough physics, but this is just to demonstrate. So this is so one layer, top layer, bottom layer. The twist is contained between this coupling between the two layers. And that's it, basically, roughly, broadly, basically. Okay, but this is not sufficient, so you need to take more number of atoms. So you will keep going, and this becomes a really large Hamiltonian to describe the flat bands accurately, let's say. Okay, so generally, for example, the system will have 600 plus 600 kind of a band structure, at least, basically, for accurate description. Let's say. Okay. Okay, so here's, so you do this, so you take that band structure, you do accurate enough calculation, you will end up with this loss function, etc. So here's, let's say, for one particular angle, theta is equal to 1.05, which is sort of like a magic angle in these systems. So here you see this, so this energy scale is MeV. So this is 0 to 50. So these are like, 10 MeV dispersing band that I was talking about. Here's the Van Hoff singularities in the joint density of states. Okay. So optical conductivity, the dielectric function. So the zeros of the dielectric function give you this plasmon modes, etc. Okay, but here's the ELS spectrum, which I wanted to talk about primarily in this, basically. So this particular angle, 1.05 degree, this is a metallic system. So even at 0 Fermi energy, there are some electronic states here. Okay? So I was anyway expecting a interband plasmon dispersing as root Q. So that is shown here, basically. Okay, so there's the interband plasmon mode dispersing as root Q as expected. But here the flat bands are also very close to each other, etc. So just at 10 MeV, you can start having this interband plasmon mode also, actually. Okay, and that is here. So if you only consider the intraband terms in the density response, then that loss function is here, which clearly deviates from the root Q behavior. Okay? So this particular mode, which is shown here, and zoomed part of intra and interband shown here, contains both combination of both intra and interband plasmon mode. Intraband, of course, you can see the fit here. It goes as root Q, but interband correlations make it deviate from the root Q behavior. So that's the main idea of this slide, basically. Okay. So lowest plasmon mode in metallic state is combination of interband and intraband plasmon mode. Okay. So then you can ask what happens if you go to a slightly different angle where you get this gapped state, etc. Okay. So here's theta is equal to 1.33 degrees, and you are in a gapped state. So you can see at the Fermi energy you have almost 0 electrons, but as soon as you go 5 to 10 MeV in the Fermi, either conduction or Valleytronics, you start seeing a lot of states. So then the transition between these 2 points basically give rise to this interband, and that's the whole spectral weight here. So if you do a separate calculation for intra and interband, you will find that there's no intraband mode, only interband mode, basically. Okay. So the highlight here is the following: that if mu is within the gap, so chemical potential is within the gap, so no intraband plasmon. Within the flat band transitions, okay, so you get this low energy interband plasmon. And of course, you can also transition from here, this flat band, which is occupied, to these Moire flat bands, and they give rise to this interband plasmon peaks, basically. Okay, and one of these peaks was actually measured in the context of TBG, twisted graphene, bilayer graphene, basically, in the experimental paper that I showed. Okay. So in this gapped state, the only mode is the flat intraband plasmon mode. Okay. Then comes, these systems are extremely tunable. So electric field can be used to tune the system. So let's start from, the magic angle system, which is 1.05 degree. for different, so delta is the vertical electric field between, let's say, layer 1 and layer 4. So 2 bilayers below, 2 bilayers on top. So delta is equal to 5 MeV, delta is equal to 11 MeV, and delta is equal to 20 MeV. So you start from here, you start opening up a gap slowly, etc. And there's an even larger gap, etc. Okay. So here you start seeing that, you get this, so this metallic state, of course, intra and interband both are there, and you get this plasmon mode, which for small q is dispersing, but for larger q is extremely flat because of, let's say, confined in the van of singularity in some very loose sense, basically. Okay. Here you start opening up a band gap, so you get a interband plasmon mode, but the spectral weight in the loss function is very, very small, so it almost hardly visible. And of course, you get this lot of higher band transitions, which give you these plasmon modes. Okay. And here you increase the gap, you see that both the intra and interband plasmon mode disappear completely. So of course, the overlap function between these two bands, basically, that plays an important role in deciding whether you get an appropriate spectral weight or not, basically. Okay. So okay. So okay, yeah. So that brings me to the end of this, let's say, talk. So I was talking about this. So when we do this calculation, we have to calculate this overlap function. Okay, so this kind of a quantity, which actually measures interband correlations, basically. So from M band to the nth band, how are they connected, basically, right? So that spectral weight, that overlap function actually dictates whether you will see this, how strongly you will see this interband plasmon mode or not, basically. Okay, so I had one more slide, but I seem to have deleted that. Okay, so with that, let me come to sort of so this is what we have studied till now. Then the next.
Amit, 20 minutes are up.
Sorry?
20 minutes are up.
Yeah. Okay. I'm about to finish, actually.
Okay, fine.
Yeah. So this is what we have calculated till now. Okay. This is another problem that we are thinking about. We have just started thinking about after we finish the calculation. Okay. So the next idea is that, can there be a acoustic plasmon mode in TDBG, let's say, or TBG also for that. In fact, in all of these twisted Moire systems, actually. Okay. And the origin of the idea is that graphene, even monolayer graphene, actually can have an acoustic plasmon mode in the system. Okay, so bilayer graphene is very well known to have acoustic plasmon mode in the system, and Rajdeep had a fantastic paper on that. Okay, but here we are talking about only monolayer graphene. Okay, so here's the, let's say, the electron energy loss function in the omega q plane, where q is parallel to the gamma k direction. And this is the regular plasmon mode. So the intraband plasmon mode dispersing as root q, etc. that we say. And there's another plasmon mode here, which is within the particle hole continuum. But if you change the interaction strength by virtue of changing the substrate, so this can come get in this region also and become undamped. Okay, so that we have actually calculated and seen, basically. Okay, and this particular mode arises from the electrostatic interaction between electrons in the two different valleys. So if I had only one valley, I'll have only one electron pocket. I'll never have this acoustic plasmon modes. Okay. But by interaction between this valley and that valley plasmon, I can get this new plasmon mode, which can also go to the undamped regime if the interactions are, let's say, strong enough, and so on. Okay. Okay, so that's the idea, motivating idea. And we expect an acoustic plasmon mode in TBG also, or TDBG, so twisted double bilayer graphene also. In addition to whatever I just described, intra and interband plasmon modes, so the lowest energy mode. Okay. And this will not be captured by the long wavelength calculations, whatever we have done here, etc. So this will need more accurate calculation, etc., which we are currently planning to do, basically. Okay. So that's one idea, and that brings me to the summary of this. So I discussed about basically the existence of low energy plasmon modes in TDBG, twisted double bilayer graphene. Exactly similar physics plays out in TBG also. Just that TBG, the electronic band structure is less tunable by electric field and so on. Okay, so we found that metallic TDBG has intraband plasmon mode, which should have a root q dispersion as expected. Plus, it has a interband plasmon mode, which skews this, which is of the same energy as this root Q dispersion, and which skews the overall dispersion basically. Okay. And this low energy interband plasmon primarily arises from this correlation between the flat bands, etc. So we are still working to understand its nature and in what kind of systems it can arise. So it doesn't arise in, for example, normal gapped graphene, even if you have a very small gap. So we're just trying to understand, what are the necessary criteria for existence, let's say. Okay. So that's some ongoing work. So there are a lot of high energy intra-band plasmon modes also in these systems, which indicate large overlap matrix element between these flats and the Moire bands basically, right? Which can go up to, let's say, 50 MeV and so on. So that is another thing we are trying to explore basically. When can I say which kind of systems, can we make some universal statements like, which kind of systems will always display this kind of plasmon modes and so on and so forth. Okay. So with that, let me conclude, and thanks for listening.
Yeah. Thank you very much, Amit, for a very nice talk. We have about 6 minutes for questions. So if anyone has any questions, just please unmute yourselves and ask. You don't need to use the hand raising tool. Just go ahead and ask.
Subrata, can I ask one question?
Sure, go ahead.
Amit, in the TDBLG, the double bilayer graphene, there are supposed to be these churn transitions as you go up,
Yes, correct.
in electric field.
Correct,
Do you see any signature in your plasmon changing?
Yeah. So that is something we have to explore actually. Okay. So this delta electric field. So that is a very nice question. So I should have shown a phase diagram actually. Okay.
That's fine.
Yeah. So this delta values we specifically choose so that we are across one of these transitions at least, let's say. Okay. So where the valley chart number changes actually. Okay.
Right.
So, but what happens is this bulk plasmon modes, do not really carry the signature of these basically. Okay. So that signature can be carried in some boundary modes. Etc. Okay. So what we have here is this intra-band and interband. So these are quite universal and not really sensitive to specific valley churn number. Okay. Yeah. So that's my feeling as of now, but not.
No, that's fine. That's fine. Just one more, very technical question. Where is your Fermi energy when you are, for example, in this plot? Is it at the CNP or are you?
So this is at CNP actually. We fixed the Fermi energy so that we are at CNP.
Okay. Thank you.
Because otherwise you cannot compare different systems.
Yeah, I understand.
Other questions? Anyone? Just unmute yourself and ask if you have a question. No? Okay, then maybe I can ask a question. So you mentioned this, I guess, several times during your talk, but I didn't quite, I'm not able to see it really in the plots. So as far as the damping, the Landau damping of these plasmon modes is concerned. So for instance, here, how exactly does the damping change with delta? I mean, where is the particle hole continuum here?
So see, that is the beauty about this energy loss functions basically, right? So the energy damping is actually, so let's go to this. So this is for graphene, let's say. Okay.
Right.
So this is the energy loss function, which actually contains the information about electron hole, particle hole excitations actually. Okay.
Right.
So this region, this black line marks this, interband, let's say, particle hole excitations. And this marks the boundary of intra-band particle hole excitations in graphene at least.
Right.
Okay? So this is the free region actually, which is completely yellow. So zero spectral weight basically. Okay. Right. So this has information, and here you see.
I see. Okay. So all right. So the color bar here is telling you.
Well, exactly. Right. So as soon as you can see this red, which is bright enough, you should be able to experimentally see it actually. So it will have.
So that's the sort of lightly damped to undamped part, and then it gets damped when it enters super.
As long as you see some red here, you will have a quality factor of roughly 10, and you will be able to experimentally detect, given sensitivity of your equipment, etc. Okay.
Right. I see. Right. And this low energy mode just going away, So what is happening there? Is it just that the particle hole continuum is going in and eating up this low energy mode?
Exactly. Yeah, that is precisely what is happening actually. Okay.
Right.
So yeah, so the next set of plots, the improved version of these plots will also have a joint density of states here.
I see.
And in that, it will become clear that this intra-band plasmon mode only comes where you have this van of singularities.
I see. Okay.
So at least the a large Q behavior here. So this is exactly at the peak of the van of singularity in the joint.
I see. Okay.
So this we so this is still ongoing work, but we sort of understand it now. So this low energy plasmon mode undamped, but it goes into this van of singularities particle hole excitation of the flat bands basically.
I see.
Okay? And it gets lost completely. But the interband plasmon mode can still be strong enough to persist for some more time and be visible somehow.
I see.
So that's the technical detail, let's say. Yeah.
I see.
But yeah, so easy thing is if you can see it here, then you can possibly see it in experiment.
Right. Okay, so we have time for one more very quick question if anyone has one. No? Okay, so if not, then let's thank Amit again.
Yeah. Okay.
Right.
So thank you all for listening. So I'll stop sharing. Huh?
Right.
Okay, great.
Okay. Right. So our next speaker is Girish Sharma from IIT Mandi, and he will be talking about unconventional superconductivity and metallic state transport in twisted bilayer graphene. So, hi, Girish. Yeah, you can maybe share your screen, and you can start, and I will give you your first alert after 20 minutes, and then the next one after 25 minutes. Okay, go ahead.
Yeah, so good evening, everyone. And first of all, I would like to thank the organizers for giving me this opportunity to share my work. So I'll be talking about the metallic state transport and superconductivity in magic angle twisted bilayer graphene. And yeah, so these are the references on which my talk is based. And I would also like to take a moment to acknowledge my collaborators with whom this work was carried out. So probably most of you in the audience might already be aware about twisted bilayer graphene and van der Waal heterostructures and Moire heterostructures. But I'll just quickly go over it in the next couple of slides just for the sake of completeness. So of course, the field of 2D materials is hot, and so of course now there are a bunch of these materials, and then people have thought about also stacking these, these 2D materials on top of each other and see what happens. And and of course, quite a while ago, it was also realized that you can also think about twisting or rotating one layer with respect to the other. So this was one of the first papers that examined what happens when you rotate a graphene on top, like you have a bilayer graphene and you just rotate one layer with respect to the other. And what they found was that just a second, yeah, that the low energy dispersion is still linear. It's like a Dirac cone, but the Fermi velocity is actually significantly smaller. And then later, this work was probably further developed by McDonald and Dixit, and they actually were the first ones to predict these magic angles, a discrete set of magic angles where the velocity, Fermi velocity, actually vanishes. Okay, and you get a strong enhancement in the density of states. And experimentally, so yeah, of course, so these are the Moire patterns. Okay. And of course, this is the band structure renormalization. So you see that the Moire wavelength is actually inversely proportional to the twist angle. And of course, at a very special angle, which is the magic angle, you get a flat band. So experimentally, this was done first by the MIT group. And so what you see here in this plot is just resistivity of twisted bilayer graphene, a near magic angle, and we see these superconducting domes, and in between we have this insulating region. And as you go up in temperature, you go from superconducting to a metallic state. And it also, of course, resembles the high TC phase right now. And that's also the reason that's why this field is so exciting. And of course, more experiments are continuing. And till date, there is no universal consensus on what is the exact mechanism of superconductivity, or the insulating state, or what is the nature of the metallic state. Okay, so, and it's likely that more than one mechanism could be at play. For example, if you see this set of plots here, I mean, usually this superconducting dome is, okay, it occurs in the neighborhood of, this insulating region here. But you can also, find this, existing all by itself, for example, here and here. And also if you see here and here. So, okay, so it kind of hints that there is a possibility that you can have different mechanisms, okay, and for superconductivity and, what is giving rise to the insulating state. So, of course, we need more experimental data and, of course, more investigation. So then now I'll talk about my work on our work on metallicity. So just focusing on the strange, or what is dubbed as the strange metal. Okay. So if you look at the experimental data, okay, so these were the first set of data which actually came out. And if you just focus on the just the metallic regime, we conclude two important features which are common. Okay, so one is the linear in temperature behavior, and this linearity actually persists much below the block horizon temperature. Okay, and this is thought to be a puzzle in even high TC, and it's actually kind of, that's why it's called it's dubbed as a strange metal, and people associate that with Planckian dissipation. And yeah, so the second feature in these experiments is that there's a saturation of this resistivity at high temperatures. Okay, yeah, so these two behaviors here are of course valid right from charge neutrality up to, and yes, here you're increasing density upwards. So right from charge neutrality all the way up to your Van Hoff singularity. Okay, so then we wanted to really examine that are the phonons really important or not? Because if you read the papers here, so of course both of these manuscripts, they conclude different reasons for this kind of behavior. So it's concluded here that it's a Planckian dissipation mechanism, and here it's just concluded it's electron phonon scattering. So what is it in reality? So with this question, we thought of first examining how important are the phonons. And so initially we just focused on just near charge neutrality. Okay, and near charge neutrality, twisted bilayer graphene can be just thought of as graphene with just a renormalized Fermi velocity. And of course, it's not valid all the way up to Van Hoff singularity, as you can see here. So if you want to think about electron phonon scattering, so we have to consider the screening of the vortex, electron phonon vortex. So this diagram tells you how the electron phonon vortex actually screened under RPA. Okay, and so this is how a general vortex is going to be screened. Okay, so in graphene you have two kinds of scalar modes, two kind of phonon modes. One is the scalar phonon mode, and other is the gauge phonon mode. Okay, so the scalar phonon mode, it actually comes with diagonals. Okay, so this G is actually a matrix here, and so the scalar comes on the diagonals, and the gauge phonon modes, actually it has this beta A sigma X, so it's this off diagonals elements. Okay, so of course the scalar modes are screened, and we found that the gauge modes are actually not screened. Okay, so this beta A sigma X, this remains beta sigma X after RPS. So that means that this gauge modes actually are not screened by the electrons. So that can actually become important contribution. So then, and of course, if you then if you go further and calculate the electron phonon resistivity, you of course get what you expect from an electron phonon scattering, a linear in temperature, and of course you can also match with the experimental data at least up to the Van Hoff singularity, at least below the Van Hoff singularity. Okay, and this here, this non-linearity here at low temperature, that's due to the electron impurity scattering. Okay, due to the charged impurities. So then, but if you want to think a little more properly about this problem, we have to actually consider the phonon modes in bilayer graphene. So you have this antisymmetric mode, okay, by which mean that the two layers move against each other. Okay, and this gauge phonon mode is actually this antisymmetric mode, which we saw that it remains unscreened. Okay, but also this mode is actually geometrically enhanced. Okay, so this is a geometrical effect, and we can understand this as follows. So if you see figure A, it's just twisted bilayer graphene, and this AA stacking points here, they form a triangular lattice. And in figure B, you are just displacing the top layer, the red layer, by a very tiny amount. Okay, so you can, so practically A and B, they are kind of indistinguishable. But if you do that, this AA superlattice, basically, the superlattice here, that actually moves by a large amount in the perpendicular direction. Okay, so a small displacement actually can cause a huge displacement of the superlattice. Okay, and this U tilde over U is actually, it goes as 1 over theta. Okay, so it's a small angle effect, and it becomes very important when theta is small. Okay, so that's actually linked to why this this antisymmetric gauge phonon mode, actually it can become even geometrically enhanced, and it remains unscreened. So this looks like the way to go further. So so then so when we studied this problem further, okay, so if you just consider electron phonon scattering, okay, so it's so of course the wave vectors, okay, of the electrons can change, okay, by emitting or absorbing a phonon, but even the band indices of the electrons can, so N and M here are band indices. Okay, and we found that energy and momentum conservation, okay, in these processes, in these two simple processes, can have important implications in TBG depending on the ratio of the sound velocity and the Fermi velocity. You know, typically this ratio is not that important because VF typically is much larger than C. Okay, but in twisted bilayer graphene, C and VF can be very close to each other, and in fact, VF can even become much less than C. Okay, because VF ideally should be 0 for magic angle graphene. So what are the implications of this? The implications are that depending on the ratio of C is to VF, you can have either intra-band transition or interband transition. Okay. So for example, so let's say this K initial here, that's the wave vector of the electron, and this Q is the wave vector of the phonon. Okay, so this dashed here, this dashed circle will give you basically the wave vector of the electron, okay, after the process. So that's the momentum conservation circle, and the solid line is similarly the electron, the energy conservation circle. Okay, so these two circles, they must coincide for any finite scattering to take place. And it turns out, if you go to these diagrams, that if V is much larger, or V is just larger than C, okay, you can have only intra-band scattering. And if V is smaller than C, you can have only interband scattering. And so it's only one is allowed and the other is forbidden, okay, at a time. So with this, then we calculated the electron phonon scattering rates, okay, and also the corresponding resistivities, and discovered that there is a qualitative difference between these two scattering processes. So if you just, so we can actually calculate these expression and some neat analytical expressions can be derived in the intra-band limit and deep in the intra-band and the interband limit. Okay, so if you see that the ratio of VF is to C, how it enters the two expressions is actually different. So there's a qualitative dissimilarity between these two scattering processes. So if you then calculate the resistivity, so this is pretty standard intra-band electron phonon resistivity, also known earlier. So of course the TBG, the Bloch-Bruneisen temperature, is of course lesser than the Fermi temperature, and the linearity in temperature. Okay, so rho versus T is linear, so that linearity persists above TBG. Okay, but in the interband process, the two energy scales are reversed. So TBG is larger than TF. And here we find that this linearity is set by TF and not TBG. So this actually provides a very simple explanation of why you can have a linear in temperature interband resistivity that persists actually much below the Bloch-Bruneisen temperature. So moving forward, then of course we've seen that scalar modes are screened and the gauge modes are unscreened, and we calculated things with respect to let's consider the gauge mode. But actually it turns out that we have to do the screening properly here. So the screening, so we have to do the screening must be dynamical. Okay, so dynamical screening of scalar phonons is important, because the energy scales of phonons and electrons in twisted bilayer graphene, they can be of the same order. So we have to actually consider the frequency dependence of the dielectric constant. So that actually raises the possibility that can there be an anti-screening of the scalar phonon modes. And that possibility comes because if you see, so this here is just the dielectric constant, dielectric function plotted okay, with respect to omega and q. So if you are somewhere here, okay, below this diagonal here, so that's the intraband case, and if you are here, then this is the interband case. So there is a region, there's a finite region here where you can have where you can actually fall into this window where your dielectric constant actually becomes lesser than 1. Okay, and if your dielectric constant becomes lesser than 1, then you can actually suspect some kind of an anti-screening effect to take place. Okay, so this is for monolayer graphene, but of course in monolayer graphene you're never here, you're always in the intraband regime. But in twisted bilayer graphene you can be here in the interband regime. But what we find is that this window actually shrinks. So as we lower the angle, and this window actually shrinks to the right. So in reality, we actually, when you do the calculation, we find that there's actually no anti-screening, and rather there's enhanced screening. So these plots are just some cuts that are just plotted here. So so this here is again for monolayer graphene, and this is for twisted bilayer graphene. So we see that that is actually in a rather enhanced screening here. Okay, if you just compare the magnitudes, and there is no anti-screening effect. So of course, anti-screening or the scalar modes can be then thrown out of the game. So next we also calculated the electron phonon resistivity as a function of the twist angle, and here we predicted that of course the magic angle is special. Okay, that's where the Fermi velocity vanishes, but also we predicted that there's a new special angle here, which we call as the critical angle, and there also you should expect a dip in the electron phonon resistivity. And at this critical angle, actually the VF and C phonon, they actually become equal to each other. And the scattering phase space, the electron phonon scattering phase space vanishes, and that's why you get this dip in resistivity. And then we also, so this is for the rigid Bistritzer-McDonald model, and this is for the relaxed model here. These two for two different types of relaxed models, considering two different models, and just some lattice relaxation effects here. And we see that this feature is actually robust to relaxation effects. Okay, and maybe future experiments may try to also investigate this particular feature and probe this particular angle. So, but finally, if we needed to compare with the experiments and make a real accurate theoretical prediction, we want to actually go beyond the Dirac approximation. So we have to consider the nonlinear effects. Okay, so then we extended our calculation, which is actually valid up to the Van Hoff singularity. Okay, by using this particular model here. Okay, and so this particular effective two-band Hamiltonian can actually model twisted bilayer graphene up to the Van Hoff singularity. Okay, and using this model, we then calculated the electron phonon scattering rates both for interband and intraband transition. Okay, and of course that's quite looks a little bit complicated here, but finally, if you do the math and then you just compare with experiments, okay, we find that the experimental observations were actually very consistent with our electron phonon scattering theory, at least till Van Hoff singularity. Okay, so here's experiment, and the solid lines are basically the results of the nonlinear model. Okay, the dashed lines are basically the results of our Dirac model. Okay, so the only fitting parameters here are this beta, which is just the electron phonon coupling, and VF is the extracted Fermi velocity here. Okay, and so we get agreement in the density dependence and also in the temperature dependence. Okay, so we get this saturation of the resistivity at high temperatures, which is actually not captured by the Dirac model. So this dashed line, the Dirac model doesn't capture the saturation and resistivity, but the nonlinear model actually captures that very nicely. And we also finally did a comparison with the Planckian theory. Okay, so here's the result of the Planckian theory. So we see that the Planckian theory actually has a very strong kind of a density dependence. Okay, and so this is something which is not seen in experiments. And secondly, the extracted value of C here, it should be typically of the order of 1 or lesser. And so that doesn't match. And secondly, the extracted value of Fermi velocity also, it turns out to be higher than what is expected. Okay.
Girish, you have 20 minutes. Oh, so you finished 20 minutes. You have another 5 minutes and then 5 minutes of questions.
Sure. So I'll just wind up. So of course, so there are these shortcomings of the Planckian theory. Okay. So, and of course, this is another plot, which actually also suggests the same thing. So this kind of tells you that at least up to Van Hoff singularity, probably it's the electron phonon scattering which is responsible for the metallic regime. So now I'll quickly talk about our work on superconductivity. And so of course, when we were thinking about this problem, of course, Bernevik and others had already given a theory that twisted bilayer graphene is a phonon-driven superconductor. So we wanted to then think about plasmons. And the reason we wanted to think about plasmons is because as you see, probably also in the earlier talk, that the energy scales in twisted bilayer graphene are suppressed down to the order of few millielectron volt. So you see that you can actually get a situation where your phonon and plasmon mode actually can hybridize somewhere here. But of course, we don't want to actually complicate our scenario. We just threw the phonons out for the moment and just wanted to ask the question whether a pure plasmon or just collective excitations, can they drive superconductivity in twisted bilayer graphene? For that, we have to actually use the Migdal-Eliashberg theory, okay, to basically take into account the frequency dependence of the dielectric function, and also you need to do the frequency dependence. You have to consider the frequency dependence of the gap function, okay, which is of course not captured in the BCS theory. So, so of course I'll not go over the technical details of Migdal-Eliashberg theory. We can discuss them later if required. So with certain approximation, for example, momentum averaging. So we basically average the interaction strength over the Brouillard zone, or with some cutoffs. And so with this momentum average, because actually when you have a plasmon-driven superconductor, only the frequency dependence is actually the key here. And if we ignore self-energy renormalization and just assume a single mode model, okay. So then in those cases, of course, you get an analytical solution, right? So, and this was the formula that we derived, and you can think of it as a plasmonic analog of the BCS formula. Okay, so lambda is the coupling strength, omega m is the frequency of the plasmon node. And if you apply this formula to the Dirac approximation, okay, of the twisted bilayer graphene, we get a neat expression for TC, and that's related to the boson frequency. RS is basically just the electron strength. That's just how strong the electron strength interaction, and EF is the Fermi energy. So you see that if RS is too small, or if EF is too small, you actually will not get a solution for TC. So, and in this particular toy model, we can also compare what is the strength of phonon to plasmon. Okay, what's basically the predicted TC. Okay, and here we plot TC as a function of density for various interaction strengths. So this kind of gave us the hope that probably we can now go ahead and do a full calculation of the Eliashberg equations. And we did that, and of course we extended it beyond the Dirac model. Okay, so that we can also go all the way up to Van Hoff singularity. So we used an effective lattice model for twisted bilayer graphene. And we also now included self-energy renormalization that we had thrown away earlier, and we also go beyond the single mode approximation. However, we retained the momentum averaging, but we found later that momentum averaging of the interaction doesn't actually make a difference. And then we get these kind of domes. So what we saw is that like near the magic angle, okay, so we have this large window of TC, and as you increase the angle, the TC increases a bit, but the window density window also shrinks, and eventually at larger twist angles, this window, the superconducting window, actually totally disappears. Okay, and this is a plot of TC versus theta for various densities. And so this dotted lines here, this dotted line, so the solid lines are the results of our full calculation, and these dotted lines are the results of our previous toy model calculation. And of course, there is quantitative difference, but it looks quite good. It's not too bad considering the set of approximations that we had done. So then, of course, lastly, we had to also.
Girish, you have 5 minutes left.
I'm done. I'm just 1 minute. I'll be over. So lastly, we also included the momentum. We got rid of the momentum averaging to reply to a referee, and we found it doesn't really make any difference. So the only thing that we have not, of course, considered is vortex correction. But yes. So that with that, I just conclude. So of course, this is a growing field, and of course, we need more experimental and theoretical studies to see what is actually happening. But at least what we found was that phonons can explain the transport data, at least in the metallic regime up to VHS, and looks like Planckian mechanism, dissipation mechanism is unlikely. And lastly, we also showed that collective excitations in principle can give rise to superconductivity in twisted bilayer graphene. So yeah, so with that, I'll stop, and I'll be happy to take any questions.
Okay. Thanks a lot, Girish, for a very nice talk. Questions? Anyone? Just unmute yourself and ask. No? Okay, then maybe I'll ask a question. So, so when you're looking at this electron-phonon interaction, what you've done so far is you've used it to explain the resistivity as a function of temperature and doping in the metallic regime. Have you thought of extending this to other transport coefficients, for instance, something like the thermopower? I mean, would you expect that if you did that calculation, then the thermopower would just obey the Mott relation with the resistivity, or could something else happen?
If you just do this calculation, probably it will obey the Mott resistivity.
Okay.
That's right. What I expect. Yeah. but we have not done that. Yeah.
Right. And I guess in this calculation, your phonons are always in thermal equilibrium, right? So there's nothing like phonon drag or anything that.
There's no, will not consider phonon.
Okay. Thanks. Any other questions? No? Okay. So if not, let's thank Girish again. Thank you very much. You can, I guess, stop sharing your screen now. So organizers, we still have 2 minutes for the next talk. Should we start right away or wait for 2 minutes?
I think we can start. If there
start?
are no questions, we can start. Yes.
Okay, fine. All right. Thanks. So our next and last speaker of the session is Gopal Dixit from IIT Bombay. And he's going to be telling us about light-controlled Valleytronics in pristine graphene. Go ahead. Gopal.
Thank you very much. I hope my voice is clear and slide is visible, right?
Yes, it is.
Yeah, thank you. So first of all, I would like to thank the organizer for inviting me. I'm not from this quantum field. Technically, I'm an ultra fast guy. And in recent years, the focus of our research is inducing, controlling, and probing electronic and lattice dynamics on its natural time scales in matters. For example, these dynamics are occurring on femtosecond or attosecond time scales. And to probe or to trigger these kind of dynamics, we use different kinds of light. For example, in these two recent publications, we have used ultra-short X-ray lights to probe the lattice dynamics in solids. In this particular case, we have shown that we can probe the lattice dynamics in silicon, germanium, and we have compared our results with the results obtained by pump probe experiments. And this is where we have probed the attosecond time scale dynamics in molecules using time resolved X-ray scattering. When it comes to quantum material, we have started exploring different recent work where we are using really intense light. I will discuss what I mean by the intense light to look what are the consequences, for example, in time resolved symmetry broken while semi-metal. We have also put a proposal forward how one can see the signature of Majorana fermions using this high harmonic spectroscopy. So both I'm going to discuss in this talk. So let's come to the main topic of today's talk, Valleytronics. So what are the valleys? So for example, let's take this two-dimensional system. This is a hexagonal system. I will come into detail what I mean by this particular system. And if you look the high symmetry points in momentum space, this looks like something like this. And these are the corners where are the high symmetry points, K and K primes, and this is the center at gamma. And if you look the energy or band structure of this particular sample, you see that at K prime and at K, you have a valence band maxima and the conduction band minima. Moreover, these energy states are degenerate in nature, okay? But they are of opposite momentum or different momentum. So the first question comes, can we differentiate these two energy points, which we can call as valleys? These valleys have a very useful applications. For example, if you think these values as K and K prime in this very simple cartoonic way, and by some means, if you can excite an electron into the K valley and don't affect to the K prime valley, or other way around, if you can excite an electron in K prime valley, not into the K valley, then these can be treated as 0 or 1. Think about in terms of the spins like up spin or down spin. Moreover, it has been proposed that if you can control these valley excitations individually, then not only you can explore only 0 or 1 state, but you can also explore the linear superposition. So this is the block sphere representation of these valleys, where you can indeed explore other possible combinations, which are very, very useful, for example, for qubit preparation or quantum computation. Okay, so what is the meaning of the Valleytronics? So if you can fulfill these 4 criteria, first of all, you are able to distinguish the valleys, then you can achieve the valley polarization. Then once you have achieved the valley polarization of a desired amount, then you can detect in some experimental setup. And once you are able to detect, the last step is left to the control. If you are able to fulfill all the 4 criteria, then you can call as we are doing Valleytronics, which literally means that doing electronics with the valley, not with the electrons charge degrees of freedom or spin degrees of freedom of the electron, but the valley degrees of freedom. Okay, so let's come back to the valley polarization. So valley polarization or valley asymmetry between the 2 valleys can be obtained either by breaking the inversion symmetry or the time reversal symmetry. So let's bring back again this sample. So here you can see that these 2 atoms are inequivalent atoms. So if I start putting these M and X, so let me call as this one M and another one is X. So there are several possibilities arises. And if you look these samples, which are called transition dichalcogenide, then they have a different properties, and the most favorable properties for the Valleytronics are these 4. They are the semiconductors with an appropriate band gap. So what people have done in the past that they use different helical lights. For example, here you use sigma minus light, and you are selectively exciting an electron into the K valleys, not to the K prime valleys. And once you change the helicity of the light, then you are addressing to the K prime valley, not to the K valleys. And there is a detailed selection rules based on the valley curvature and the magnetic moment. And one can get it into all kind of details, why one valley is coupled with the one helicity of the light, another valley is coupled with the another helicity of the light. One can look into this paper, and there are other detailed literature for such kind of selection rules. But let's come back to the graphene. So this is a graphene. Unlike in the previous example or material transition dichalcogenide, here the inversion symmetry is preserved. Okay, and if you look the band structure at K and K prime points, which are the high symmetry points, there is no band gap. So this is a Dirac semi-metal and 2D Dirac semi-metal, and here you can see there is no band gap. So there is no possibility to excite an electron from a lower level to the upper level. So this kind of excitation possibilities can be immediately ruled it out. So then what it means that graphene with 0 band gap and 0 valley curvature and identical dispersion near the bottom of the valleys, it seems that graphene is not suitable for Valleytronics, which is a very, very uncomfortable or disappointing conclusion in the view that graphene exhibit exceptional transport properties, and graphene is the first 2D material that has been discovered. Of course, people have come up some alternative solutions by breaking the inversion symmetry of graphene, either by creating a heteroic structure of graphene with HBN, or let's say putting some kind of dopants or putting some kind of strain, and in this way you are just destroying the sample itself, and you are not talking about the graphene but something modified graphene. So what I'm going to convince you that there's a very simple and elegant way to achieve the valley polarization, and in a controlled way in a pristine graphene without breaking its inversion symmetry, either by creating a heteroic structure or by applying different kind of bias voltage or strain. So this is energy contour of your graphene. So this is your K valley, this is your K prime valley. And if you look in the vicinity of these valleys, you see isotropic ring structure. But as you move away from this isotropic structure, you do see an isotropic trigonal structure, which is different in these 2 valleys if you put a particular direction. So if I look this direction, if you follow my cursor, then you see that these 2 are having a different energy landscape, and that's what we are going to exploit to get a desirable valley polarization in pristine graphene. So what we have done, we have come up with a very clever combination of laser pulses. So here what I'm going to use, this is called bicircular laser. So I'm going to use a combination of left-handed circular polarized light and right-handed circular polarized light with two different frequencies. And if I look the little slow figure of this combined laser pulse, it has a threefold symmetry. And if I start exchanging the helicity of the two light pulses, that threefold structure remains unaffected. And moreover, if I introduce a phase or delay between the two light pulses, then what I can do, I can start rotating this threefold structure of the total laser pulse. And you can see that at 0, it has this threefold structure, and 180 return back its original position, but at 90 degrees, it flips back. Okay, so let's see how this threefold structure is going to induce a valley polarization in this pristine graphene. So this is my momentum space structure, and let's see at phi is equal to 0, this is the phase difference between the two laser pulses, and you see that this laser pulse fits very well with the one valley, but it is not matching with the symmetry of another valley. Once I change this value of phi, then I do see that it fits with the another valley, but not to the one valley. And this is what we have exploited to induce a significant valley polarization in pristine graphene. Okay, so here is the result. So here is my definition of valley asymmetry parameter, which is the population difference between the two valleys in the conduction band once the laser pulse is over, normalized by the mean value. Okay, and here if you see, these are the values of the phi at 0 to 180 degree, and you see that this valley polarization, which is shown in the red, it oscillates back and forth as a function of phi, and you can see that as my total electric field returns to its original position at 180 degree, so my valley polarization also give the same value at 180 degree, and at 90 degree it flips back to the another valley. So you can see this periodic modulation in the valley polarization. Moreover, this green line shows that there is no valley polarization up to a certain value of my laser intensity, and this is simple because if my laser intensity is small enough, it will not exert a significant force on the electron, and the electron is going to see in both the valleys the isotropic region. So it means that I have to have an intensity enough so that electron will start seeing the anisotropic region of this valley. Then only a valley polarization will start showing up in this graphene. So you need an intense laser. Of course, the intensity of the laser is below the damage threshold of this sample. That's what we have checked it. Okay. So now here what we have plotted, that this is the axis which we have wavelength, intensity of your light, and this is the wavelength. And you can see that either you can keep the intensity low and you can increase the wavelength, and this is the region by which you can have a valley polarization up to 60%. And the same data is plotted into one dimensional, and you can see that up to a certain value of your laser potential, vector potential of your laser pulse, or the electric field of your laser pulse, you don't see any significant valley polarization. But once it crosses to a threshold value, you see a linear increase into the valley polarization. And this is consistent with your common knowledge from the quantum mechanics. Once you have a light in presence of, your matter is exposed in presence of light, your momentum P changes to P plus AT. So your momentum is following this linear behavior of your P plus AT, right? So this is where we have achieved a significant valley polarization. Now, so, okay, we can achieve the valley polarization. We can select the valley. Now, how to probe the valley polarization and without any background? So the probe again comes from an optical means. And here what I'm going to use a high harmonic generation. So before I go and show the result, let me briefly explain what is the high harmonic generation. So let's say this is a simple solid represented by this two band. You bring a light, intense light. So what happens is induces a transition from valence band to the conduction band. And here the frequency of your light is not resonant with the band gap. It is much, much smaller than the band gap. So either you can achieve this transition by multi-photon way or by tunneling. So electron has reached to the conduction band and hole is left in the valence band, and your light is still present. So then they will drive the hole and electron in their respective bands. So that will create an intra-band current, as well as once the direction of your laser is going back and forth, like you see here. So it will possibly recombine with the hole. This electron can recombine with the hole and it generates the radiation. So the total current that comes out by this process contains two contributions. One is the intra-band current and one is the interband recombination current. And if you see the typical spectrum of your high harmonic, it is a very interesting feature, and it has all the possible signature of your band structure. So this cutoff is consistent with the minimum band gap in your material, and the first band gap at this prevalence zone is this cutoff, and then this is the next band gap, which is the maximum band gap that can be reached by your laser polarization. And using high harmonic generation in solids is not a very old field, it's hardly 10 years old, and people have seen several interesting features in solid. For example, block oscillation, which had been proposed almost like 90 years, 70 years back, but it had never been realized in solids at ambient conditions. So by using this high harmonics, I'm going to show that how I'm going to probe the valley polarization. So this is the high harmonic spectrum of graphene exposed this bicircular field, and you can see that your first and second harmonics are following the polarization of your left-handed and right-handed, and the third harmonic, the sixth harmonic, and the ninth harmonic is absent. And this goes back to a very special selection rule, because one light is your omega and another light is your 2 omega. So the total is 3 omega. So all the harmonics multiple of 3 because of some special selection rules are absent, which I can explain at later after the talk if you are interested. So you can see that this is a pristine graphene and you have no valley polarization. Okay. And if you look these harmonics as a function of your subcycle phase of your two lasers, you see that your harmonics are oscillating. And if you resolve this fourth harmonics, for example, at K and K prime, then you can see that at a particular value of phi, either the harmonics or the current is originating only from the K values dominantly or from the K prime values. The same is true for the fifth harmonics and so on. So what is the idea? That you bring a new laser pulse with the frequency 3 omega, and you see that once you have a 3 omega, so you will see a first nonlinear response at 6 omega from this harmonics. Okay, and here you can see that the strength of the two valleys will be same when there is no valley polarization, and if there is a valley polarization, then you will see the amplitude of these sixth harmonic is different. Moreover, these two contributions are oscillating at different phase. So this is a very clean way or a background free way to measure the valley polarization. So I hope that I have convinced that you can induce a valley polarization in pristine graphene using light. You can control the valley polarization. What I mean that you can hop between K and K prime values. You can also control the amount of the valley polarization, and you can probe the valley polarization. Now, recently we have come up another alternate way. So what we have come up, you don't need a bicircular light to induce valley polarization in graphene, but what you can have a asymmetry of your laser pulse that can be imprinted in your graphene. So what I mean that you have a very short pulse. So this is called a few cycle pulse. So here you have 3 laser cycles, and this is the envelope of your laser. So this is called subcycle phase or carrier envelope phase of your light actually. So you can, so the maxima of your envelope coincide with the maxima of your laser cycle, and this can be tuned, and you can see that at 90 it flips back. Sorry, at phi is equal to pi value, it flips back. And this is the way that you can control the CEP of your laser light. And this is a really a single cycle or 2 cycle pulse. So here are the results. When you have this single cycle laser pulse, this is the vector potential. And you can see that this laser pulse is asymmetric in time. So upward is less and downward is more. So you can see this is a valley polarization. The definition of valley polarization is same what we have seen earlier. So here you can see that you can achieve valley polarization more than 50%. It oscillates from one value to another value as a function of 180, which goes back to the this result that at 180 this goes back to the other direction, so it connects to the other value. But once you increase the number of your laser cycles from 1 to 3, you see that your valley polarization immediately declines significantly. The reason is simple, because now the up and down components are pretty much symmetric, so the valley polarization diminishes drastically. So I hope that you are convinced that now by using different tailored lights, we can control valley polarization. Moreover, this valley polarization can be read out in a background free way using high harmonic generation. Now there's an outlook why the light is so powerful, which is not possible with other ways like Hall effect or magnetic field or many other ways. So here is the light. So, you know, the operational speed of all your semiconductors in various electronic and optoelectronic devices is limited by several gigahertz. So this is what we call as a clock speed. And if you convert these gigahertz, this you can easily convert into oscillation as a 1 billion oscillation per second, which is the upper limit of your operational speed of computing. Instead of using a conventional way, if you use a light waves perform several 100 trillion oscillation per second, which is 3 to 6 order of magnitude more than what you have seen in the clock speed. So it is obvious to employ light to oscillate to drive the electronic motion. Unlike the conventional methods, light wave not only initiate the electronic motion, but control the motion on its natural scale. That's what we have seen in this example, that we can control the valley polarization the way we wanted. And this natural time scale is the attosecond time scale. So, and this is a non-dissipative way, okay, because the frequency of your light is not resonant with the band gap or anything. It is much, much smaller. This one.
Gopal, 20 minutes up.
Yeah, so with that, let me conclude that light-driven electronics has the potential to increase the operational speed of devices and computing by orders of magnitude, and opens a new avenue called petahertz electronics, which is a very fancy topic these days, which people are doing. And recently we have explored possibility to explore petahertz electronics in spin polarized way. So in nutshell, what we are talking about petahertz spintronics in this paper, where we have looked the spin polarized effects in hexagonal boron nitride. With that, let me conclude my talk. Part of the work was collaborated with Professor Misha Ivanov and his group in Max Born Institute, Berlin. Most of the work was done by Dr. Mrdul, who had just graduated from my group. This is the advertisement in my group, and thank you very much for your kind attention. So
thank you very much, Gopal, for a very nice talk. Questions, anyone? Please unmute yourself and ask. Yeah, sorry. Rajdeep, do you have a question?
No, I didn't have a question. I just
okay, I have a very general sort of question. So since you were talking about petahertz electronics, I mean, you know, so the idea is to use sort of higher frequency electromagnetic radiation like light rather than microwave radiation, right?
Yes.
Okay, so in general, I mean, aside from looking at pristine graphene, if I wanted to exploit this property of light to get very high switching speeds, what property should the material have? I mean, if you
earlier what people thought that material should have some band gaps, but it's not needed, because earlier a few years back people always thought that graphene is not suited for this purpose. What we have shown, and there's a experimental work going on, so we have a preliminary data. So band gap is not a constraint. So the only constraint that the intensity of your light should be below the damage threshold of material, so that it don't destroy the matter. It does not convert your matter into plasma. And there are works few years back where people have driven the current, for example, in SiO2, even in some of the materials where they can control, let's say, the metallic to the insulator phase and back. So they can control what phase they want by light. So it's like a reversible process. So they can go to, let's say, the insulating to the conducting phase, and when they change the direction of your light, they can come back to the insulating phase. So it's like a coherent control. So you are really controlling the way you want.
Right. Okay. Thank you. Any other questions? Okay. If not, then let's thank Gopal again. And with this, we can conclude the evening session, and I guess also the day's proceedings, unless the
So we would, So we would like to thank all the speakers of this session and the chair, Professor Subrata Mukherjee, for coordinating this session, and actually all the speakers today. We have another very tight schedule and hopefully very interesting day ahead tomorrow. So we will